Okay, let's do problem number 25 on page 99 in chapter 4. And here is the problem right here. It says one 3.2 kilogram paint bucket is hanging by a massless cord from another 3.2 kilogram paint bucket. It's hard to say. Also hanging by a massless cord as shown in this figure here. If the buckets are at rest, what is the tension in each cord, the top and the bottom cord? And if the two buckets are pulled upward with an acceleration of 1.6 meters per second squared by the upper cord, calculate the tension in each cord. So let's do that. So I've kind of got it set up a little bit here. And let me zoom in a little bit. So we've got these two buckets. I didn't draw this very well, but two buckets, and they're hooked together by these cords. They have identical masses, and we want to know what is, I'm going to call this tension 1 and this tension force 2. And we want to know what are these tension forces if the acceleration is 0, and what are these forces if the acceleration is 1.6 meters per second squared. So I kind of got started here with part A. And that is, I'm going to find the tension force for cord 1. And what I'm going to do here is I'm going to take these two buckets and I'm going to combine them into one free body diagram. And I can do that. You can do that. And so if I do that, I'm going to draw the tension force pulling up. And I've got the weight pulling down. But this is the weight of both buckets. It's pulling down on this cord, right? This upper cord, if you think about it, it's supporting the weight of both of these buckets. So the mass that this has to support is the combined mass. This, which 3.2 plus 3.2 is 6.4 kilograms. So that's the mass that we have to go. Now in part A, it was given that the acceleration is 0. So when I sum the forces in the y direction equals 0, this is 0 because it's given that the acceleration is 0. So now I can solve for the tension 1. And that's going to be equal to just mg, which is 6.4 kilograms times 9.8 newtons of force for every kilogram of mass. And so I did a calculator. 6.4 times 9.8. That's 62.7. Newtons. Right? Cool. Now we want to find for the middle bucket, and so what I'm going to do there is I'm going to draw the middle bucket, or I mean the bottom bucket, this one right here, and so here's that, and it's being pulled up with a tension force. This tension force here is pulling up on this bucket, and of course we've got gravity pulling down on it. Now, how much, so this is my free body diagram. Now, notice that this tension force only has to support the weight of the bottom bucket. So if I sum the forces in the y direction, they're going to be equal to 0 because it was given that in part A that the acceleration is 0. And it's just the same thing, ft2 minus mg, right? This is positive, this is negative. I'll make this positive y, the positive y direction. So this is going to be F2 times g equals mg, which is equal to 3.2 kilograms times 9.8 newtons per kilogram. So that tension force is good. Well, it's going to be half of that, right? 3.2 times 9.8, and we get 31.4 when I round it off. Okay, cool. All right, now let's do part B, and I'm going to fit it over here so I can fit it all on one paper. Now, everything's the same, except that now when I look at this situation, when I sum the forces in the y direction, it's not equal to 0 anymore, right? It's equal to MA. So I've got the tension force minus mg equals ma. So when I solve for this tension force, you know, from here, this tension force, I'm going to get ma plus mg. So the tension force is equal to ma, which is, again, it's 6.4 kilograms, times 1.60 meters per second squared, plus mg, which is 6.4 kilograms, times 9.8 newtons per kilogram. Now you could, if you wanted, you could factor out the 6.4 kilograms and then add 1.6 to 9.8, and that'll work. But let's see, 6.4 times 1.6 equals 10.24. And then I know this is just 62.7, so plus 62.7 equals, and I get 72.9. So look, here's what this means. The tension force, this tension force right here, this one, now it not only has to support the weight, like it did in part A, but it also has to provide an additional force to make it accelerate. See? So the tension force, yeah, it's still equal to the weight, but you have to add the force required to make that mass accelerate. So it's going to be a greater value, and it is. Now, for the bottom bucket, you just do the same thing. I'm just going to start here, minus mg equals, but it's not 0 anymore, it's ma. So we get the same equation we got before, like up here, but now the mass is, of course, is half as big. ma plus mg. Now I'm going to show you, I'm going to do it a little bit differently. I'm going to factor out the mass, and this is a plus g. So the mass is 3.2 kilograms. Okay, that's the mass on my free body diagram here. And then A is 9.8, I'm sorry, 1 point, it doesn't matter what order you add them in, but I want to stay consistent. So the acceleration here is 1.6 meters per second squared plus, now g, I usually write it as 9.8 newtons per kilogram, but a newton per kilogram is also 9.8 meters per second squared. Same thing. So this is going to be equal to and when you punch that in, you get 36.4 or 36.5 if you round it off. So that's our answer. So let's back up and look at the whole thing. Zoom out. So here's the key idea in this problem. Here we've got two objects linked together, and if I want to know what this force is, I can just make the objects one free body. You know, I can combine these two buckets into one free body diagram and figure out what the tension force is. When I don't have any acceleration, you sum the forces and set them equal to 0. But when you do have acceleration, you sum the forces and set it equal to ma. And then for this bucket, you just draw a free body diagram of this thing like it's all by itself, which I did over here. And then you can solve for it. If there's no acceleration, the tension force is just equal to the weight of that bottom bucket. But if there is acceleration, it's equal to the weight of that bottom bucket plus the force required to cause acceleration, the net force. And so that tension turns out to be 36.5. Anyway, if you have any questions, please bring them to me in class. That is all.